Calculus, section 5.5, looking at the substitution rule. Okay, so in the substitution rule, we're first starting to talk about these indefinite integrals. Okay, so we have more complex things going on. We're not going to have a numerical answer. We're actually going to have our function answer that we're going to be relating with. One of the things that we had issues with, and remember back when we started taking derivatives, is what happens when we have multiple functions going on. We had to use chain rules. So if we had a function within a function, we had to take the derivative of what's inside times the derivative of the overall function. Well, now what happens is we try to inverse these functions. Well, that's where the substitution rule comes in. So we see that in a substitution rule, basically what we start noticing is we notice that g prime is continuous on an interval and f is continuous on a corresponding range of g on that interval. So as we look at this, we see that our g prime is appearance and it's inside an overall f function. Well, what we start doing is we start using a U substitution rule to kind of go backwards and work with just the integral. So if you notice, we don't have an overall from a to b in here, we just have an integral. So we're just working with the variables themselves as we consider the problems. So, substitution rule, change variables. Given an indefinite integral, okay, indefinite means that we don't have a upper and lower, or lower and upper bound. We don't have any bounding in here. We're not on a very specific interval. We're on everything. Okay? Given an indefinite integral involving a composite function, f of g of x, identify the inner function u equals g of x. Okay? Such that the constant multiple of g prime of x appears in the integrand. Okay, so basically we're going to take the inner function, we're going to let that be u, and then if the derivative of that inner function then should appear somewhere else in that function, so that we can then bring in our u equals g of x, and then our du equals g prime of x dx. Because once again, the derivative of u with respect to x, if we multiply by that dx over, that's why du equals g prime of x dx in that integral. Then we'll evaluate the new indefinite integral with respect to u, and then we'll write the results in terms of x using u equals g of x. Now, not all yield the substitution rule. So don't think you're going to be using this on every single problem out there. Don't think that every single complicated problem has this capability to use. There are other theorems and values and different things to use out there, so do be well aware that things don't always go perfectly on here. Okay, now if we start talking about a definite integral, okay, definite integrals are a little bit different because they have a lower and an upper bound. Okay, so if we start using U substitution, once again, we're trying to find a value on here. We're trying to find that net area, because that's what that definite integral tells us. It tells us that net area. Because we're doing this, and we're now changing that function to be f of u, what we have to do is then we have to apply a and b into that g function, that inner function in here. And we're actually going to change these values on here. Now, the main reason here is because once we evaluate this integral, we can substitute these other values in right away rather than going back to the original one and then going. Now you could do it either way. Both are going to yield the same answer, but it's just something that we want to be well aware of as we're considering these problems and working through, that we always want to work the easiest and fastest way possible, because that's what calculus allows us to do. It allows us to manipulate things in a different way of thinking using our advanced operations, and so we can quickly get to our answers. And that's what we're doing here. We're taking this very complex function, we're breaking it down into a simpler function. We're taking our upper and lower bounds, transitioning them to be on that different interval of which we're working with, and then we can just evaluate this fully right away, and we don't have to go backwards like in an indefinite integral. You have to go backwards on there because there is no value you're trying to find. You're doing it for all possible intervals within there.